always easy. So we give this a shot, okay? Your study guide. Evaluate the following limits if possible. Confirm limits algebraically. Some limits are not able to confirm algebraically. We start out here. I see x in the numerator, x in the denominator. Those are the highest powers. Can anybody tell me right off the bat what is the limit going to be? 3/2. I know that right away. As I simply divide the top through by x, I get 3 minus 4 over x. As I divide the bottom through by x, I get 4 over x plus 2. Now, as x goes infinity, I think Kelsey kind of had an aha moment here a little while ago. Where is Kelsey? Oh, she's out there. She said, well, what does this mean? You know, x going to infinity, how do you know it's 0? Well, if you plugged in a number like 1 billion, and that's what I did with her, 4 divided by a billion is basically what? 0. It's not. And so your graph will never actually touch 3/2, but it gets darn close to it. And so this gets darn close to 0, and so does this. You're right. It doesn't equal exactly, but it gets so stinking close that for all practical purposes, we say that's the asymptote that it approaches. So sure enough, 3/2 is what I'm left over with. Okay, here we have x squared on top, x to the third on bottom. Where's my bigger power? It's on the bottom. So right away you should know where this is going. Either positive or negative infinity. The bottom is going to get bigger ridiculously faster. I'm sorry, go to 0. The bottom gets bigger ridiculously faster than the top. So you're going to have a huge number on the bottom and a very small number on the top after a while. I mean, come on, take the number 10. If you square 10, you get 100. If you cube 10, you get 1,000. 100 over 1,000, that's 1/10. That's very small. Try plugging in some bigger numbers. All you have to do is divide the top by x squared. 8 over x squared minus 5. I'm sorry, we're dividing by x to the third. 8 over x to the third minus 5 over x divided by x to the third over x to the third is 1 plus 4 over x to the third. So I have 8 over x to the third is 0. 5 over x is 0. I have 1 plus 0. So really what you have here is 0 over 1, which is 0. All right. Limit as x goes infinity, 3 sine of x. Sine of x looks like this. Okay? It does not exist. It oscillates back and forth between 3 and -3 the entire time. Sure. Limit as x goes, we can't confirm it algebraically. Limit as x goes infinity, x squared minus x. Some people like to plug in infinity. Well, you get infinity minus infinity, which is 0. Look at the graph. What does the graph look like? Parabola that goes up. As x goes to infinity, what does y go to? How about as x goes to negative infinity, what does y go to? Yeah, so you have some knowledge about the graph, don't you? Let's just confirm it. When you want to confirm it with a polynomial, simply do this. Factor out the largest term. If I factor out an x squared, I get x squared times what? 1 minus 1 over x. Look at how easy that is now. 1 over x goes to 0. 1 minus 0 is 1. Question? Excellent question. This is like x to the first power, right? If I factor it out, I will subtract exponents. 1 minus 2 is -1. If you distribute this x squared back through, you will get that. You will get that. On the top, when I factored out or when I divided it, yeah, I could divide the top and the bottom by the same thing. That's why that worked. This works because this expression is still equal to that expression. I just factored something out. So I'm left with x squared times 1, basically. And as x goes infinity, if you square infinity, you're just going to get a bigger number, right? It's going to be positive or negative. Positive. Beautiful. The bottom. Anybody know what it goes to? 1/3. Very good. The answer is infinity. Because x goes to infinity, you square it, you get an even bigger number, bigger infinity, times 1 is infinity. Okay, so E, if I factor out an x, or if I divide the top by x to the 4th, limit as x goes to negative infinity of top divided by x to the 4th would be 2 over x to the 3rd minus 3 over x squared plus 1 over 3 plus 1 over x minus 1 over x squared plus 1 over x to the 4th. Or x to the 3rd, excuse me. Right? So what do these guys do? They go to 0. So you got 0 plus 1 on the top, which is 1. On the bottom, you've got 3 plus 0, which is 3. So this thing's going to go to 1/3. No. In this case, you have just a polynomial. So what we're going to do is we're going to factor out x to the 3rd. Yep. So this one can trick people. I got x to the 3rd. So I'm going to have 1 plus 2 over x minus 1 over x squared. So that's what I got. So I factored out x cubed. What does this go to? 0. What does this go to? So you got x to the 3rd times 1, which is x to the 3rd. Now think about this, you guys. I'm sorry, we're plugging in negative infinity. Negative infinity. If you cube negative infinity, you get negative. You get a negative. Okay? Very good. Very good. So if you know, now in your book, we had some more complicated problems. As you notice, I haven't put any of the study guide, and they will not be on the test. This is really confined to your content limit. Yes. Yeah, actually, it does apply in this case to tangent as well, secant, cosecant. They all have periods where they repeat themselves. And so they don't ever approach a single number. Yep. In their basic forms, yes, we can manipulate them such that they would have, for example, if you had this, if you had sine of 1 over x as x approach infinity, that would approach 0. So that does, but that's different, and I'm not asking those, okay? All right? Okay. A for the day. Identify how differential calculus may be used to determine the following. How can you tell if a function is increasing? Excellent. F prime of x must be greater than 0. How about decreasing? F prime of x must be less than 0. How about concave up? And F double prime would be concave down if it's negative. Well, that would be too easy of a question on the test, right? Question. Right, and if we get a negative value, then we know it's decreasing. Right. When you plug it in, when you plug that x value in. So let me just ask you a question real quick. Let's say I have this: f of x equals negative x to the 4th plus 2x, and I want to know, is it increasing or decreasing at x equals 1, and is it concave up or concave down at x equals 1? You tell me, how would you do that problem if I asked that? All I would have to do is find the derivative. F prime of x is equal to negative 4x to the 3rd plus 2. And I would take the double derivative. So f double prime of x is equal to negative 12x squared. So if I plug 1 in, 1 to the 3rd is times negative 4 is negative 4 plus 2 is negative 2. So it looks like it's negative. So it's going to be decreasing. It's decreasing at 1. that means that we have a local max or local min if you were to get 0. That's why I didn't specify equal to 0, because that would be a local max or local min point. Neither increasing nor decreasing. I won't ask that. Okay, and then concave up or concave down, I would plug in 1. If you plug in 1 and square it, you get 1 times negative 12 is a negative, so it is. So it's decreasing and concave down at 1. We just use a first derivative and second derivative test to see that. We're gonna do that, yeah. Does anybody have questions on that? Is that pretty straightforward? Use a first and second derivative to verify whether it's increasing or decreasing at a point. That question will be on the test tomorrow. I promise, because I wrote it last hour. Identify the following characteristics. I left some things out here. Oh, you should add this. You should add this. How about x-intercepts and y-intercepts? Let's start there. If I want to find a y-intercept, that's the easiest one. How do I find a y-intercept? Plug in 0 for x. And if you plug in 0 for x, 0 to the third minus 6 times 0 squared, yada, yada, you get 0. Y-intercept is 0. How would I find x-intercepts? I set it equal to 0. 0 equals negative x to the third minus 6x squared. Factor out a negative x squared. 0 equals negative x squared times x plus 6. Looks like I have a double root at 0. So 0, 0, and negative 6. I'm not going to make you write the 0 twice, but I do, because it helps me identify I have a double root there. I like that. Something math teachers get excited about. So there we go. I've got those two pieces. So I know where it crosses. Now, intervals of increasing and decreasing, what do I have to do for that? Find that. When in doubt, just derive it. So f prime of x is equal to negative 3x squared minus 12x. And I set that equal to 0 to find out when it actually changes value between increasing and decreasing. 0 equals negative 6x minus 12. Whoop, I'm taking the derivative again. Yep, I'm taking the derivative again. I'm getting carried away. Negative 3x times x minus 4. So that means that I have critical points. Critical points means something interesting happens at 0 and 4. Whoop, plus 4. There you go. Thank you. So 0 and negative 4. So who can tell me my intervals for this problem? What? Good. And then I want to see whether f prime of x is positive or negative at these values. And so I test it using the derivative, or negative 3x times x plus 4. So I'm going to plug these points in there and see what I get. And if I do this, I get what? I get a positive times a negative, which is a negative. I get a positive times a positive, which is a positive. And then if I plug in, say, 1, I get a negative times a positive, which is a negative. So it looks like I'm decreasing here, increasing here, decreasing here. So we've got from negative infinity to negative 4. And then I've got from 0 to infinity, increasing from negative 4 to 0. Awesome. Anybody have questions how I get a first derivative and find those intervals? We've done that before, haven't we? We've done it before. We had good practice before break. In Taylor Blake's words, the most difficult test of his entire life. Which he still managed to get an A on. That means he's the smartest person in the world. So, concavity, I need to do the second derivative. Colleen Thompson loves the second derivative. Ori Shirley loves the second derivative. That's who loves it. What a great guy. Negative 6x minus 12. Everything. 0 equals negative 6x minus 12. So f double prime of x is negative 6x minus 12. I set it equal to 0, and you get x is equal to what? 12 equals negative 6x. So x is negative 2. So what are my intervals? And negative 2 to positive infinity. You guys are so smart. And now I use that, negative 6x minus 12, to determine something about f double prime of x. Where is it positive? Where is it negative? Tell me something interesting. I plug in negative 3, I get a positive. So f double prime of x is positive, and then I plug in, say, 0, and I get a negative. So it looks like it's concave down from negative 2 to infinity. Concave down, negative 2 to infinity. Concave up, infinity to negative 2. Now we come to something where you got to wrap it all together. My guess is everybody can do that, right? But now let's make sense of this. Local max and local min. Where do they occur? 0 and 4. First derivative points tell us local max and min. Our critical points at 0 and negative 4. But which is which? Well, a local max is concave. A local max is concave down. So let's check. At this point, 0, I'm sorry, negative 4. Okay, we'll check this negative 4. Okay, so I use my first derivative piece where I got, where I factored this, and I got 0 and negative 4 out of it. Okay, here it is. Here's my work. 0 and negative 4, I'm going to use those two. Which interval does 0 fall into? Does 0 fall into concave up or concave down? 0 falls into concave down, so 0 is where you have a maximum. Does negative 4 fall into concave up or concave down? Concave up. And concave up is where you would then have a minimum. How would I find out how far up or how far down? I plug it into the original function. If you plug in 0, you get 0. If you plug in negative 4, you get negative 32. Right? Into my original function. That gives me location. The inflection point occurs where the second derivative is equal to 0, which happens at negative 2, which you notice is right between the local min and local max. The inflection point occurs where the second derivative is equal to 0, which we found was at negative 2. And to find location, I would plug in negative 2. And if you plug in negative 2, you get negative 16. Yep, that gives me location. Here's a point of confusion for a lot of people. What about asymptotes? Do polynomials have horizontal and vertical asymptotes? None. If you approach infinity, y will go to infinity. If you approach negative infinity, y will go to negative infinity. Not, well, or the other way around. I mean, it's just, they approach infinity from either sides. They're polynomials. That's what they do. Yeah? 1 point. In this one? Oh, that there's none? The derivative is never equal to 0 in the second one. You have a critical point where it's undefined. Okay, so last thing, I'm going to sketch a graph. And because I go all the way down to 32, I'm going to go up and down to 40. And you guys, this should be the most exciting piece. Because now what we get to do is we get to check this against our calculator and see how good of a drawing we can create. And so I'm going to put negative 5, positive 5, 10, negative 10. And I'm gonna plot my zeros. I have zeros at 0 and negative 6, so I got 0 or negative 6, excuse me, and I've got the 0 spot right there. And it looks like my local max is at 0, 0. Oh, I've already plotted that. My local min is at negative 4, negative 32, which is right about down here. And my inflection point is negative 2, negative 16, so -2 and about -16 would be right about here. So I've got these points. That's where it changes concavity. So as I draw this, now again, the reason why I think that that's just so interesting is because if we just take that to scale on our calculator and I type in y equals -x to the third minus 6x squared, and I put my window to -10 and 10 and to -40 to +40, I get a graph that looks ridiculously similar to that. No graphing technology needed. We did that by hand. We should feel pretty proud. How do you like them apples? Yeah. Okay. Any questions on that one? So I have a problem with a basic polynomial that you need to approach on the test tomorrow. Can you do that? Sounds like we're batting 1,000, people. Sounds like I need to make this test harder. Okay. Yes. You do need to remember it. I do expect you to remember. I do expect you to remember. Okay? I mean, I will make the list for you, but you need to know what you use the first derivative for. You need to know what to use the second derivative for. I will give you the list of things you need to find. I will not ask you to find symmetry. I will ask, I give you this, so, yep. So if you study your sheet, and now I'll add x and y intercepts, okay? No, we won't worry about domain and range. Okay, x intercepts occur where the function is equal to, where the function's equal to 0. So I look at the top. Where's the top equal to 0? At 0. And the y-intercept occurs where x is equal to 0, correct? So if you plug 0 in for x, what do you get? 0. So what do you know? This thing goes through the origin at 0, 0. Yeah, if I do set this equal to 0, it'll come out. And I know that so easily because where the top is equal to 0, the whole thing's equal to 0. Yeah. Now, I'm going to go straight to the asymptotes. I have vertical asymptotes that occur where the function is undefined. Where is it undefined? X equals 1. So I have x equals 1 is a vertical asymptote. I have a horizontal asymptote that occurs where x approaches positive infinity and negative infinity. So let's investigate this. Let's take this thing, the limit as x goes to infinity. I should divide the top and the bottom by x. Negative 2x over x is negative 2. X divided by x is 1 minus 1 over x. 1 over x goes to 0. So you're left with negative 2 over 1, which is negative 2. So my horizontal asymptote is y equals negative 2. Now the rest of this is actually very easy for this problem, and you'll see. It says show your work. I guess I should look at intervals of increasing or decreasing. So I find f prime of x. In order to find the derivative of this, I need to use the, which is a wonderful thing. And so in order to use a quotient rule, I take the derivative of negative 2x, which is negative 2 times the bottom left alone, x minus 1, minus negative 2x times the derivative of the bottom. What's the derivative of the bottom? 1 over the bottom quantity squared. So that means that my derivative is actually equal to negative 2x plus 2 plus 2x all over x minus 1, that quantity squared. What happens? Two x's cancel. I get f prime of x is equal to 2 over x minus 1 quantity squared. Please follow along with what I say, because I'm going to say something that is going to help some of you, hopefully won't confuse any of you. First of all, where is the critical point that exists? 1. 1 is the critical point, because it's undefined in the denominator. Can the numerator ever be equal to 0? No. So my intervals are from negative infinity to 1 and from 1 to infinity. You sure can. You can do 2 over x minus 1 quantity squared equals 0 over 1. Cross multiply and solve. What's going to happen with this piece? 0. And you just get 0 equals 2, which is no solution then. Right? That times that is 0 equals 2 times 1 is 2. You get 0 equals 2, no solution. This thing is never equal to 0. Never. So so what this tells us is where the first derivative is equal to 0 is often where you have local maxes and mins. There are no local maxes and mins on this thing. The derivative is never equal to 0. Furthermore, I need to test f prime of x here. Before we test it, let me just ask you something. Is 2 always positive? Yeah, if you square something, is it always positive? True or false? This derivative is always positive. True. So you could go ahead, plug in 0, and then plug in 2, and verify that's positive. Fine. But if you look at this thing, it's always positive. I dare you to find something to plug in and get a negative result. You can't. It's impossible. Positive, positive. Where's this thing increasing? All the time. Negative infinity to 1 and 1 to infinity. Where is this function decreasing? Never. I don't have any points where the derivative is equal to 0. Do I have local maxes or mins? Never. That made quick work out of that, didn't it? So let's, yeah. Not necessarily never. You could have a graph that looks like this. Let me just show you one. You could have a graph that looks like this. You know, and so you would have a critical point here at 0. I'm not going to give one like that to you, but, you know, you did encounter a problem like that in your homework where, you know, you found that you had some interesting stuff going on here. So, I mean, you know, so this is interesting right here. But that's not what my graph looks like. How do I find something about concavity? I take the second derivative, the double derivative. Let's do that. F double prime of x is equal to, do you like the quotient rule? Let's get rid of it. Can I show you a trick? Well, 2 over x minus 1 quantity squared, true or false, is the same as 2 times x minus 1 to the negative 2. Now I just have to use the chain rule. Before I'd use the quotient and the chain. Now I just have to use the chain rule. Is that nice? So that means that f of u is equal to 2u to the negative 2, correct? And u of x is equal to what? X minus 1. What's f prime of u? Negative 4u to the negative 3. What's u prime of x? Derivative using the chain rule would be equal to this times this later, buddy. So you get negative 4u to the negative third, or negative 4 times x minus 1 to the negative third, which is negative 4 over x minus 1 to the third. Now, you guys, when I did the answer key, I used the quotient rule just because that's what we've always been doing. But I mean, you know, that's kind of the, you know, as you mature in your mathematics and in your understanding, you see that there's multiple ways to do things. I like that a lot more. I think that's nicer. So we've got this, -4 over x minus 1 to the third. Tell me, can the top ever be equal to 0? You don't have any inflection points then. Because the second derivative is not equal to 0. But you do have spots where the second derivative is undefined. Where's the second derivative undefined? 1, which is not surprising, and 1 is carried through the entire way. So we do have intervals from -infinity to +1 and from 1 to +infinity. Okay? And so I need to check those with my second derivative and find where f double prime of x, what the value is. So if I plug in a number, let's plug in, I like 0. 0 minus 1 is -1 to the third is -1, and -4 divided by -1 is positive. So it looks like it's concave up here. And if we plug in a number here, I'll plug in, say, 2. 2 minus 1 is 1 to the third is 1. -4 divided by 2 is -2. It's negative, so it's concave down there. So -infinity to 1 and 1 to infinity. Concave up from -infinity to 1. Concave down from 1 to infinity. Now is the fun part. We get to draw it. It's awesome to draw this thing. We have 1 and -2. So I'm going to make some sketches here. Be real careful with my tick marks. See if I can look exactly like my calculator. X is 1, so I got this vertical asymptote right here. And I got this horizontal asymptote at y equals -2. I know it has x and y intercepts at 0. Now, I don't have any other points to plot. I just know, here's all I know. That's concave up on this side. So if I draw it against the top part of the asymptotes or the bottom part of the asymptotes, which one would give me concave up? I got to draw it on the top part. That gives me this concave up shape. Well, I guess you know that anyways because you know it goes through 0, 0, right? So I guess that was easier. And we know the second part is concave down. Well, you can't follow these asymptotes and get concave down. You have to do these bottom ones. And here's something I think is really neat, how many ways math tends to verify itself. Look at this. As I move my finger along this graph, am I increasing or decreasing? Increasing, 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 increasing. And now I have to jump down here. Am I increasing or decreasing? It's always increasing, you know, and it verifies it. The algebra always shows that it's true, which is pretty neat. Well, the backside, you guys are really good at these problems. I mean, you guys know how to do 5, right? Number 6 is a tough one. That's tough. Oh, gosh. 6 is really hard. I'm going to have to go through that really quick. We got -4, we got +4, we got 4. That's an equation for a circle, right? But the top half of the circle. So an equation for a circle, you guys all remember this, right? X squared plus y squared equals r squared. My radius squared is 16. Right? If I solve for y, if I solve for y, I get y is equal to plus or minus the square root of 16 minus x squared. Subtract the x squared over square root both sides. Now tell me, if I'm looking at the top half, am I looking at the positive or the negative? I'm looking at the positive. So y equals positive square root of 16 minus x squared. So that's great. So now I've got these points here. I'm going to inscribe this wonderful rectangle where I got -x, I got positive x, and then I've got this point here, and it's x comma square root of 16 minus x squared, because my y value is equal to that. So area is equal to length times width. How wide is this thing? No. How wide is the box? 2x. How tall is this thing? Sure. How tall is it? It doesn't matter either way. Square root of 16 minus x squared. You guys are going to love this. So what I have is I have area in terms of x is equal to 2x times the square root of 16 minus x squared. So you just have to now do one thing. Take the derivative and set it equal to 0. And then we solve it, right? Promise you won't yell at me. How do you take the derivative of that? Chain rule and the product rule. What's the derivative of 2x? 2 times the square root of 16 minus x squared. Oh, hey, we're halfway done with the product rule. Plus 2x times the derivative of that. How do I find the derivative of that? Chain rule. Let's see. So I've got f of u is going to be equal to u to the 1/2, right? No, it's not. So this is my function. So this is u to the, this is a positive 1/2. When we take the derivative, we'll get a negative. So we got u to the 1/2. What's u of x? What's the inside part of my function? 16 minus x squared. And then f prime of u, what's the derivative of u to the 1/2? 1/2 u, the negative 1/2. That's great. And then what is u prime of x? Negative 2x. So in order to find the derivative of the whole thing, I take u prime of x times f prime of u. So I've got negative 2 times 1/2 is just negative 1. So it looks like I got a negative x. I'm going to try to rewrite this just a little bit here. I got this 1/2, so I've got 1 over 2 square roots of u times negative 2x over 1, right? I mean, that's kind of what this is saying. So it looks like my 2's will cancel. I'll be left with a negative x over the square root of u. Square root of 16 minus x squared, right? So that's that derivative. So this guy goes right here. So let's finish it off. If you know, when the bell goes, if you want to go lunch, that's fine. If you want to see the rest of this, I'm guessing it's going to take about another minute and a half. So I've got 2 square roots of 16 minus x squared plus 2x times negative x over 16 minus x squared, the square root of that. That's my derivative. We set the derivative equal to, and we solve. So this is really 2 square roots of 16 minus x squared over 1. And then 2x times a negative x would be a negative 2x squared. So minus a 2x squared over square root of 16 minus x squared equals 0. Well, hopefully you guys see where this is going now. This works out really, 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 really nice. Yeah, exactly. Taylor Harris sees, if I just add the 1 to the other side, 2 square roots of 16 minus x squared over 1 equals 2x squared over the square root of 16 minus x squared. So I just added the 1 to the other side. Taylor Harris now wants to cross multiply, so I get 2x squared on one side. And when I cross multiply, what happens to the square roots? They go away. I get 2 times 16 minus x squared. Well, that's not bad at all. 2x squared equals 32 minus 2x squared. Add my 2x squared to the other side, so 4x squared equals 32. Divide by 4. X squared equals 8. Square root both sides. X is equal to plus or minus the square root of 8. So now you can solve the whole problem because you know that this spot right there, that's the square root of 8 right there. No, you can't look angry or upset. You have to look amazed at saying, what a wonderful thing that calculus allows us to do. I mean, how else would we solve that problem? Oh, you want to, okay. Well, oh, square root of 8 is 2.83. Uh, double it to get your width, right? Right. So the width is equal to 5.66. If you plug this back into y, you actually get 2.83 again. And if you multiply them, if you plug 2.83 into y, or into x to get y, that's your height. So, and the area is actually 16. Well, you sure can do that.